So we have this idea of a limit, but we can only really calculate limits using their graphs at this point, or by just plugging in values. Of course, plugging in values is really another way of saying finding the graph, because every time you plug in a point, that gives you a piece of the graph. But it turns out that in many cases that we care about, just plugging in values or looking at a graph really isn't sufficient. For a couple examples of that, let's start with this one. So let's find the limit as x goes to 0 of sine of 1 over 1000x. And if you look at a graph of that in your favorite graphing tool, it might look something like this. So you see the graph just sort of comes from far to the right and far to the left. We're heading towards 0, so it just comes into the middle here, and it looks like it's just heading towards 0. So shouldn't this be 0? I mean, it looks like it on the graph, but, limits only care what happened near this x value, 0, and in fact, they really only care what happens extremely near this x value, so maybe we should zoom in. If we zoom in a little bit, well, something is starting to become visible here. There's some sort of wiggle up and down, right? It looks like to the left it goes down and to the right it goes up. So it looks like maybe this limit doesn't exist because from the right it's infinity and from the left it's minus infinity. But wait, that can't be right either because this function has a sign in it, and so it should top out at 1, and the smallest it should ever get is minus 1. So, I don't know, let's zoom in further. If we zoom in further, well, you can see that something weird is happening. What's going on here is that as x gets very, very close to 0, this function starts to just go up and down extremely quickly. And in fact, the closer you get to 0, the faster it goes up and down. So this function isn't, as we approach x equals 0, this function isn't settling down on a single height. And so our initial guess of 0 was totally wrong. This limit doesn't exist at all. Okay, so lesson learned. If we're going to use a graph, we should zoom in, at the very least. Okay, let's look at one more example. How about the limit as x goes to 0 of the square root of 4 minus x squared minus 2 over x squared? So if we graph that function, it looks like this. And let's see, it's a little hard to tell exactly where this is. Maybe if we zoom out a little bit, it'll be easier to see. It looks like this is as x goes to 0, it looks like the height is about a quarter. So maybe about a quarter. We'll put a question mark on that. We've learned our lesson from the previous example, which is we should probably zoom in to see if anything funky is going on. And as we zoom in, it seems like it looks okay, but, we can keep zooming in more and more, and yeah, once we zoom in far enough, we start to get this stuff. So this looks kind of similar to what happened in the previous example, where when you get close enough to 0, the function just starts jumping around a whole lot. So that makes us think, well, no, maybe this limit doesn't exist after all, right? Because the function just jumps around when you get extremely close to 0. Zooming in any further won't do us any good because, well, it's starting to slow down as I zoom in, and that's because the computer's actually having trouble drawing all the mess that's happening here. So we've kind of reached the limit of what we can get at just by using a computer, but in fact, we've missed part of the story here because all this bobbing up and down that's happening, the real graph doesn't actually do that. It turns out this is just an artifact of how the computer is rounding things as it does calculations. So in fact, this limit does exist. In fact, it's not close to a quarter, it's exactly a quarter. We don't have the tools to prove that yet, but it's a fact. So, the problem here is, with these two examples, the first example, it seemed to bob up and down because the function actually does bob up and down. In the second example, it seemed it bobbed up and down not because the function did that, but because the computer was having trouble giving us an accurate picture, because it's just a computer, right? It has to involve some rounding error when it does those sorts of calculations. And in any particular example, you won't necessarily know the difference, right? So I guess what we should do to remedy this situation is come up with tools for calculating limits exactly that don't depend on using approximations for graphs. So we really need to figure out calculations and not just approximations.